Alright, this problem is most quickly answered in part A by using technology. Let me show you that first, and then I'll show you the manual way. So we're going to do second distribution, normal CDF. And what you do is you put in the lower bound, the 61.9, comma, the upper bound, 62.9, comma, and then you put the mean, mu, 62.6, comma, and then you put the standard deviation of 2.7. And just like that, you get 0.1465, which is the correct answer here. And so that's the fastest way to get to this answer. Now the alternative manual method, if you don't have the technology, you're going to have to do this manually for the two numbers. So you use z-score, which is x minus mu divided by sigma. And in the case of the first number, you start with the 61.9 minus mu, 62.6, and then you divide by sigma, which is 2.7. Alright, so let's calculate that. So rounded to two decimals, that's negative 0.26. And now we do the same thing for the other z-score for 62.9. Alright, so we'll calculate that. And so to finish that calculation, it was 0.11. Alright, so now, again, this is all from manual. If you have the calculator, we're already done, but for the manual one, you have to go get your tables. Alright, so let's go to the z-scores. We need to get negative 0.26. Alright, so we go to negative 0.2, 0, 1, 2, 3, 4, 5, 6. So 0.3974 right there is our number. That's the number we need. Now likewise, we're going to do the same thing for a z-score of 0.11. Now that's a positive number, so we scroll down on our formula sheet to positive z-scores and go to 0.11, so 0.5438. Alright, so we found our two areas, the area with negative 0.26 and the area with negative 0.11. So now we take the difference between those, 0.5438 minus 0.3974, and when we get that, we'll get 0.1464. And so it's going to be very close to the right answer, and there is tolerance here within this bound to accept data from the table or data from the calculator. So although these two don't exactly match and it says it's really 65, it'll accept 64. Alright, and so that's how we do it, and that's why it says round to 4 decimal places, because if you go pull the data off the chart, it's by default to 4 decimal places. And just a refresher on rounding, if you do the calculator version, you get 0.14651. If you need to round to 4 decimal places, you go to the 4th place, which is 5. You look one number to the right, which is 1, and you realize that's less than 5, so you basically throw away all those numbers. And if this number 1 was 5 or greater, then you move the 5 up to a 6. You would call it 0.1466. Alright? So that's how you do the rounding for that, just to make sure we're all clear on rounding to 4 decimal places. Now for part B, we're going to use central limit theorem. Alright, so central limit theorem says that for a sample, the standard deviation should be the original standard deviation divided by the square root of n. So in our case, our sigma was 2.7, and we're going to divide by the square root of 7. Now central limit theorem is a difficult thing to try to understand. I gave a link in another video, but in fact really all you need to do is go to khanacademy.org and do a search for central limit theorem. And it'll explain why this is what this is and how it means, what it means in real life, and how we can understand it. But when we take a sample, we can expect a different mean, perhaps, but if we take a lot of samples and take the means of the sample's means, we get a normal distribution, and this follows. But for now, I just need to calculate 2.7 divided by square root of 7. And so I get 1.0205. Now we're going to do the same calculation we did for part A, but do it with a new sigma. And so I put all the same numbers in that I did for part A, but I changed sigma to be 1.0205, and that's where you get 3